Hello, all. Can you hear me? Can you hear me?
Yes, we can hear you.
Yes, sir.
Okay, cool. So let's wait for 5 minutes because it will keep popping up. Um, this and I need to allow. It may create some disturbance. And yeah, so thanks for joining. Today we will cover some very basic stuff on image processing and in general manipulating the tensors using NumPy. So we will have a session with aspect of practicality and followed by a few problem solving sessions. Right? So, what I mean by that is we will have a Jupyter notebook where we will show how these algorithms in general work, you know, and then followed by a few problem solving. Okay, so let's wait for 2 more minutes and we will start. So any questions you guys can ask. So feel free to ask. Otherwise, I mean, there is no point in having this thing. Um, and I might not be able to explain every aspect of it because I don't know what exactly could be the problem. Right? If you ask, I'll try to. Um, Okay, so I think let's get started. I'm sharing my screen. Please let me know if you can see it. I will share my entire screen. Let me know. Can you guys see the screen?
Yeah, able to see.
Okay. So yeah, what are we discussing today is a package called NumPy. It's a very powerful system to manipulate the tensors in general. Okay, so yeah, you can simply install NumPy using pip by following this command. And don't worry, these notebooks will be uploaded in the respective folders. Okay, so you will be having access to this, and you can simply import it. And yeah, so there is that uh, objects in this NumPy called as arrays. Okay, so this is a 1D array, and this is a 2D array, and this is a tuple. if you guys can allow the people who are joining, can you please check that? Because I have to keep toggling between the tabs.
We are getting the prompt, but not sure. We'll try.
Yeah, because I don't want to toggle. I can disturb you.
Yeah.
Right. So yeah. So np dot arrange uh, is a way of creating an array by specifying the start and end point and the increment. So here it starts at 5 and with increment of 2 and stop before it hits 15. And linspace is the way of uh, producing numbers between 0 and 1 in 5 equally spaced terms. Right? So that's what you get here. And np dot zeros will give you a zero matrix of 2 rows and 3 columns. Similarly, np dot ones of 3 comma 2 will give you all one matrix of 3 rows and 2 columns. And np dot I of 3 will give 3 cross 3 identity matrix. And np dot full of 2 cross 2 is the 2 cross 2 matrix, all filled with 7. And yeah. Yeah, what are the types of things that once we create an array will have, right? One is the shape. The shape is like, were you guys able to allow people?
Yes, sir. We are able to.
Yeah. Okay, cool. If you can do that, that's great. Anyone can do that. That's great. Yeah. So what are the attributes, right? One is shape and one is the type and one is the dimensions and this size. So let's run this and see what's happening. So there's a 1D array, 2D array, 3D array. So remember, one 2D array will have two 1D arrays. Like this 5, 6 is a 1D array and 7, 8 is a 1D array. And this is enclosed within uh, uh, another this thing, right? So this, I mean, what I meant to say is two 1D arrays when concatenated it forms a 2D array. Right? That's what I mean. And similarly, 3D arrays, you can imagine this thing, right? It's a concatenation of the 2D arrays. And if this is a 2D array, right? And this we are concatenating two 2D arrays. That's it. Okay. And let's see, like 1D array shape is 4 comma. So if a 1D array will have a shape of the length of the elements, just comma, that's it. And for a 2D array, say, okay, let's go to other attributes. So what is the data type is int64, D type, you can access it. And how many dimensions it has, because it's a 1D array, it has one dimension. And what is the size? It has a number of elements of 4. Again, coming to 2D array, you can access the shape of the array by 2 comma 2, and the data type will be 64 in 64, and number of dimensions is 2, and array size is 4. You have 4 elements. And similarly for 3D array, I'm not going to this thing, it's a sign. And yeah, how do we do the indexing of the arrays? Once we create an array, now this section talks about how do we access the elements of the array. Right? So if you see, right, this is the 1D array and this is a 2D array. Now, 1D array, a array of 0 will be access the first element. So remember, this is, I mean, if you are familiar with MATLAB kind of language, it is a one-based indexing, but this is not one-based, this is zero-based indexing. The first element starts with 0. And 2 will give you the third element, that is 30, right? 10 and 30. And similarly for the second, this is just like a matrix, this thing operation. So 0 means the first row and 1 means the second column. The second index means the column. So 0 means you pick the first of this array and 1 means you pick the second, right? So you understood what I meant here. The indexing of the 2D array. If not, I can go over it quickly again. Why it has picked the 2D here. Yes, no. You want me to repeat? Yeah, this notebook will be shared. And yeah, if you can speak, that's better because I have to toggle the tab to see the messages. So yeah, can you guys please talk because I don't want to toggle between the notebook and you to read your messages, the Teams tab. Okay, so 1, 2, 3, 4 is a matrix. Just imagine this 1, 2, 3, 4 is a matrix. Okay, let me write this. So 1, 2, 3, 4, and this is a matrix. You are asked to locate the element 0, 1. This is A. You are asked to locate this element A of 0, 1. So 0 corresponds to first row, and 1 corresponds to the second column within the first row. So this is the first column, this is the second column, right? So this is 2. And similarly, the second point was 1 and 0. So 1, can you guys tell me what would be this?
Second row, first column.
Yeah, what is the element in this matrix?
Number 3.
3.
Cool, right? That's it. Now the slicing. Let's say we want to extract a subpart or subportion of an array. Okay, how do we do it? So this is the way you slice it, right? 1:3 means the end number doesn't count. So 1 and 2 indices will be accessed. Okay, so what I meant is, so this is 0, 1, 2, 3. 10 corresponds to 0, 20 corresponds to 1, 30 corresponds to 2. Okay, okay. Yeah. So it is 1 corresponds to 20 and 2 corresponds to 30. That's it. So on the last index won't be printed. Okay. So 1 to 2. That's it. 1 is to 3 is 1 to 2. And for this 2D array, it is the same thing. Say it is what is asking is you are printing the entire first row, right? So that means where is this? Yeah. So A of 0 corresponds to the entire
now
0
disconnected.
row. Okay. Can you come again? What was the problem?
County is now connected.
Okay. So yeah. So similarly, this is the second thing is asking the second column of your 3D matrix, right? So what would be the second column here is 2, 4, and you can see that 2, 4. Okay. So this is another um, parameter is try to how many elements you want to skip in between, let's say, right? So this is try to you skip the one element every alternate. So 1D array of if you give a stride of 2, it first prints 10, skips 20, 30, it skips 40, and there's nothing to print. So that's why it gives you this thing, uh, 10 and 20. And if you want to reverse the rows and columns, right? So this is the way, this is the command. You just flip the rows and columns, right? So if you see 1, 2, 3, 4, 1, 2, 3, 4. Let's flip the rows. What you end up getting is 3, 4, and 1, 2. Now, if you flip the columns, you end up getting 4, 2, and 3. Okay, that is what is being shown 4, 2, and 3. That's it. So this is the command to attain that. You just want to flip rows, just do this and don't do anything here. You don't do anything here, just the rows will be flipped. Now, the Boolean indexing. Let's say I want to get filter an array based on such certain condition. Right? Here we want to access all the entries that are more than 25. Right? So you just need to give a condition that you have want an element greater than 25, and this returns the indices. This greater than 25, and again access using the same array, you get this 13. And this need not be sorted. Here it is sorted, but even though it is not sorted, you'll get the elements. Yeah, and this is another way of you can specify the indices any random order, and it will print in that order. Okay, so 0 means 10, and 2 means 30, 1 means 20. Yeah. Okay, and yeah, so with NumPy arrays, you can do almost all the operations: addition, subtraction, division, exponentiation, matrix multiplication, etc. Right. So here, if you see array 1 plus array 2 just adds the element by element of two arrays, just right, 5, 7, and 9. A subtraction, simple subtraction. Multiplication is okay. And we need to be careful here. It's an element-wise multiplication. The 4, 10, and 18. Okay. So if in linear algebra, if you are familiar with Schur products, like something called as Schur products, that's an element. It is denoted like this. So it is defined for any matrices AB. You multiply element by element. So if you use a star operator in writing in an NumPy and give multiplication of A and B, any two tensors, it performs this thing. Okay, so this is called the Schur product. Okay, so far so good. Any questions? Division is straightforward division. Make sure that entry in the below one doesn't have any zero, otherwise you end up hitting an error. Right? And exponentiation, you want to square, cube, do anything, just specify double star. So 1, 2, 3, double star 2 is nothing but 149. Okay. Yeah. Any questions up to this point?
For exponentiation, can it be a float?
I think so. Yes. 2.3 also works. Yeah. Should work. Yeah. Yeah. It can be true. Any question? I think you just need to be careful only when this array in the division. During division, in the one going to the denominator doesn't have, make sure it doesn't have the zero. Even division is an element wise here. 1 over 4 is 0.25, 2 5 is 0.4, 3 by 6 is 0.5. Right.
Can you change that array 1 to a negative number? I am just when I have a negative number in there, exponentiating.
Yeah. Anything. See, you did array 1 minus array 2. And
No, exponentiation gives a NaN actually.
Exponentiation is fine if you have a negative number. If you do a square root, it's a problem. Yeah, it's a square root. I think it's a problem, right? Yeah, anywhere you encounter square root sign, that should be a problem. That will be a problem. And yeah, so there are some functions, simple functions that are provided within the package called NumPy. right? Sign. You can mention the array, right? And it just brings the value. And for the exponentiation, you can do np dot hp. Whenever you do np dot log, it is considered at the base is equal
Sir,
to each. Yes.
sir, can you hear me?
Yeah. I can hear you. Yeah.
Sir, in exponentiation, can we use something like int max or int min, sir, just like in C++?
I don't know. Okay, what do you mean by it? Can you just bit more elaborate?
Sir, like infinity, sir. Infinity.
Infinity, okay.
Sir, can we use infinity in the exponentiation? That's what I'm trying to ask you.
I don't think so. Whenever you hit infinities, right, you end up something called as max, and you should avoid it. That's precisely like I said, even if you do 1/0, you end up sitting an max.
Oh,
Basically, whatever you are performing, it was a 64-bit or whatever. Here it's a 64-bit. Right. So whenever your representation maxed out all the bits, so at max, what is the highest number you can represent is when you get 64 bits, 2% the total range. If it goes beyond it, you end up hitting a man.
okay, sir.
Okay.
So
So
just wanted to
yeah,
check.
another yeah, yes,
I just wanted to check in this trigonometric operations.
yeah.
Ida. Sir, is it my voice is audible?
Yes, it's audible. Yes.
Sir, in the trigonometric function, the input array you have given as a one-dimensional three elements. One is 0 and pi by 2 and pi. If you apply in
Right.
sign operations, sign
Right.
of 0 is 0, understandable. Sign of non-zero
Okay.
is 1. But again, np dot pi, third element is non-zero, but it is 0 dot.
Yeah, and it is close to zero. Right? 1 in minus 16. 10 power minus 16. What that means? 1 into 10 power minus 16.
1 to 10 power. So it's close to 0. So you just
Close to zero. Yeah.
okay. But since it is a looks like a real number representation, we could have just given some representation, right? Like
Yeah, and it all depends how this package is implemented, right? They might be having something to compute these signs. So typically, what happens is the sines and cosines are implemented using the Taylor expansion. Okay.
okay.
Sin x is approximated as x minus x cubed by 3 factorial plus x plus 5
No, I
by
understand the
and
point.
so
If it is almost like a 10 to power of minus 16 is even
right.
more than a negative side of the trillion or more than a nano size.
Yeah.
But since it is a form, floating point representation is given that can be represented just like an even for a cursory sake, they can be represented like a floating point, right? For calculations, it's fine, but just showing an
Yeah.
output is what I'm asking. Like what is shown in the cosine minus one dot so and so many dots, something e plus
Right.
something like that. Nothing else. That's not a great question actually. It's just a representation.
I mean, whatever is being considered inside us that's printed. That's it. And there's nothing much to look into it. Right? It's practically zeros, as you said.
Yeah, yeah.
Yeah, and it's a matter of just printing. I don't know. Yeah. Okay.
Yes, sir. Fine.
So this is an important concept, broadcasting. So just pay attention to it. All right. So what is happening is,
Sir, just before that, can you just share this notepad? Sorry, are you doing it on a Colab or a Jupyter, sir?
so this is a Jupyter.
Jupyter.
I'm
If you
running
would you
this
mind
in my own
just
system.
share it in
Yeah,
the Colab,
this
copy paste and
is
share it in the Colab. We can also go through and run immediately and see.
so I'll paste this notebook in a file where you guys can access the materials. Right. So you can go home and you are at home, wherever you are. Just access it, run it.
Sure, sir. Just
Okay.
an advice, nothing else.
Yeah. Anything else?
Yes, sir. Please continue.
Yeah. So basically here, right, what is happening to this? I think there's some. Okay. Yeah. So this is a broadcasting operation, right? So what is happening is now each entry of no, this has a shape of 3 cross 1, right? The array 2, right? Because you have three elements, three one-dimensional elements, and within each of this, it's only a single entry. This is a single column, right? 3 rows and 1 column. Now, whenever you add a row to a 2D matrix, each entry gets added with the entire row. Now, this is a broadcasting operation. This is called as the broadcasting operation. Operations of this sort, right? So this is like 4, 5, and 6, right? And we are adding this thing, 1, 2, 3, and each of this will get added to this element. Okay, so something like this. And similarly, if we specify it equals to array, like 1, 2, 3, 4, and one-dimensional array, right? And you multiply them, right? So what happens is each row of your 2D matrix gets multiplied element by element with the second array, right? So 10, 40, again 30, and 80. Right. So basically, what's happening here is second array is expanded like this internally. 10, 20, gets repeated 2 times these rows as the explanation is given, and then the normal this thing is performed. Like similarly here, the array 1 gets expanded to 2D array by repeating itself 2 times. Okay. Um, Yeah, so another coming to other topics is manipulating the NumPy arrays. So this will give you elements coming from 0 to 11. Right? Whenever you specify a size, you get the entries 0 to size minus 1. Okay. Now, what does the reshape does is this tensor 0 to 11 it resizes to 3 comma 4, and resizes happen row wise. The rows I meant 0 1 2 3 will be considered as the first this thing row. You have 3 rows, and 4 5 6 7 falls in the second row, and 8 9 10 11 falls in the third row. Okay, and again flatten it, it comes back to the same thing, the same array. And remember, there's something called as the Ravel, which also flattens. But what it does is it doesn't create a copy of your the original array and give it back. So it maps. It still maps it. Basically, what I meant is, let's say this is flattening, right? And you just print it. Okay. And now what you do is after raveling, just make this changes. Okay. So if you modify the first element and then print, right, the new array, the this index has gone to 99. It's changed. But when you do the flattened array of 0 to 88 and you print the new array, right? New array is still the same as what you have modified here. So it doesn't, it's like a pointer, right? Ravel is like a pointer. If you change the original one, the whatever is being mapped, the Ravel, okay, that is getting changed. But flatten creates a copy and then assigns. Okay.
Sir, if you don't
Yeah.
mind, can I ask one question, sir?
Yeah, sure.
Sir, in the you said it's a Ravel new array,
Hmm.
and you print it,
Hmm.
and it is showing a one-dimensional array, and then you are assigning first element as a 99, but why it is showing as a 3 by 4 in the second print output?
Because new array is nothing but your 3 cross 4 matrix. So instead of flattening, you are raveling.
Correct, but the new underscore array dot Ravel you have given and assigned a new variable. It's called raveled underscore array.
Yeah,
And
that's the point, right? That's the point. That's the point. It's not a new variable. It is not copying. It's just like mapping. It's like a pointer.
okay, but
But
whereas
that's not the
flatten,
case
Sir,
with the class.
whereas flatten make a copy.
Exactly.
So the previous state of new array is a 3 by 4 which you have created earlier,
Right.
and it got updated. Okay,
Updated. But when you change the flatten, it doesn't get updated. The new array is whatever it is.
okay, okay.
sir,
Thank you.
Yeah.
sir, in the flattened array, you have shown that you are changing the first element as 88, sir. Can you please print me that flattened array so that I can see that visually and understand?
Okay.
Yes, sir. Yeah, understood. Thank you.
Okay. Yeah, the next topic is just transposing the arrays. It's just the transpose, regular transpose of transposing the matrices, right? And the fancy way of doing across dimensions is use the swap access. Okay, you can just swap the entire this thing, the dimensions. And what else? Yeah, joining and splitting the array, especially the most
Sir, the swap array, sir, just one
yeah,
thing.
yeah,
If it is a
yeah,
multi-dimensional array which is having our
yeah,
data set, sometime like it
correct.
goes up to 30 columns or 40 columns, the rows up to 16,000. If you want to make it as a three-dimensional aspect, moving from 2 to 3D, that is possible, sir.
No. I think for that you need something else. Um,
Okay.
yeah, you need to probably use the reshape or resize commands, right? Like one thing you remember the first example you shown
We
0 to
gave
11,
40
you
to
shown
2D. Yeah,
3 to 4, right? Yeah,
yeah.
so you have to do that and make sure the total number of entries
Should
should
match.
match when you multiply all these dimensions. Right?
Okay.
Okay, so yeah, so this npic.concatenate is the most frequently used this thing. Typically, while processing this data, you may end up in situation you want to concatenate multiple data points, data sets, or what, right? So this is 2 cross 2 array matrix, right? I mean, whenever you use NumPy called as arrays, and when you use something called as PyTorch, you call as tensors, right? So yeah, I may end up using this nomenclature interchangeably. You don't get confused. Yeah, this is again, what is this dimension? Anyone can tell me?
It's essentially adding the one-dimensional array as a third row in the array one.
Right. So, uh, when you are doing this operation, right? Okay, this will run fine. Make sure the other dimensions are intact when you're concatenating on one dimension, right? The first time you were able to concatenate and end up getting 3 cross 2. Now, if you see concatenating, it throws an error, right? What I meant is the column dimension. So you are concatenating on the axis 0, right? And it worked because the dimension on the other axes are consistent. So whenever you try to concatenate on a particular axis, make sure the other dimensions are matched. That's the key point. That's why I did this thing. Okay. So first of all, yeah, these are split. I haven't used yet, but maybe you guys want to try, you can try. And yeah, these are some commonly used things. The most frequently used are resize also. Yeah, resize, repeat. Unique finds the unique elements of an array. If you do 1, 1, 2, 3, 4, let's say, right? So it's like a set operation. But set if you do set of something, you'll end up a set object. But if you do np.unique, you end up getting the array which has this unique elements. Yeah, we are here. Okay, fine. Yeah, so this is again same thing as the multidimensional array. Right? Where we already used multidimensional array in the other context earlier. Yeah, this is the way of declaring a multidimensional array. And similarly, you can declare this three-dimensional array. And you can initialize with zeros and ones with arbitrary number of dimensions. Right, so yeah, how do we index in multiple dimensions is the same thing, right? 2D
Sir,
arrays.
is there any way of this is doing a very raw deal? Is there any way conditionally to make it split 2D into 3D? On particular condition matches, only that row I'll add it as a third dimension.
You should be able to do it. I'm pretty sure. I mean, right now I'm not able to. I may not be able to exactly tell you, but probably maybe next week we can do it, or maybe you can try once we upload this thing. Almost pretty much that you can think of, which is correct. You should be able to do it NumPy. It is that powerful.
Okay. Because this looks very raw
Right.
operations.
Yeah. This is just an indexing as we have done with the 2D indexing. This is just a 3D indexing. What else? Yeah, what the matrix operations, right? You can do the matrix product with the dot and mat null. And yeah, both will give you the same results. I think it has some mat null performs some more checking, I think. Basically dot, right? With the np.dot, you can just give two 1D arrays and just do it. It just do the inner product and give you the answer. But I think with MatMel, you need to properly convert it to say 1 cross and then n cross 1. That's the difference. And yeah, sometimes you may end up utilizing the random number generations, right? Random numbers you may want to use. So what are the tools that NumPy provides in dealing with the random numbers? So np.random.rand gives the samples a number from the uniform distribution. Right? Uniform distribution is between 0 and 1. Okay. And np.random.rand5 gives you a array with 5 elements, each sample from a uniform distribution between 0 and 1. Any questions on this? I can go over.
Sir, random numbers are not within the floating, but within a positive range or a negative range possible?
It is positive, right? 0 to 1 only. Right?
No.
You can adjust the mean accordingly.
Random number generation, this is a floating point standardizing from 0 to 1. But I want a given
Yeah,
range, 1 to 100, 1 to 1000, 1 to 10,000.
It's good. It's coming up. It's coming up. Yeah.
Okay.
That's you want to generate integers, let's say between 1 and 10. So last number is typically not included. Right? So it generates from 1 and 9. You end up getting, say, here you got 4. And yeah, and you can mention the size also, like between 1 to 101 and size is 3 cross 4. In a 3 cross 4 matrix or array, it prints the numbers between 1 and 100. Okay.
So offbeat topic, the random number that has got generated, if you want to see the distribution of the random number generated, can I plot a random number?
Yeah, you can plot. You can plot. So you have to generate not 10 or 100. You have probably may end up generating some tens of thousands of numbers and then plot the distribution.
And plot the graph.
Yeah. Maybe do a histogram, right?
Yeah, histogram will be even better. Yeah.
And then you should be able to find. If you have more number of data points, then make the bins of histogram more finer, right?
Finer also I can
look better.
Okay.
Excuse me, sir. Sorry to interrupt.
No,
I
no,
actually have some interview to be taken, so I'll need to drop off. Like, will these sessions be recorded and be available later?
I'm recording this.
Okay, they'll be available to watch later, right?
Yeah, I will upload a YouTube onto YouTube and will provide you a link.
Okay, sure. Thanks a lot, sir. And I see multiple sessions going on at the same time. I think another session started at 3 to 5. Like, are all the students the same? Or?
Yeah, more or less we have decided we'll go similar content, but the the way we explain will be different. But we have decided the content has to be similar. Will be mostly the same.
Okay.
Something might be different here and there, but yeah, almost 80 to 90% it will be same.
Okay, fine. Okay. Sure. Thank you, sir. Thanks a lot.
Okay, so this is the uniform distribution, right? You guys are familiar. I'm assuming you guys are familiar with standard normal distribution, right? Gaussian distribution. Okay, so to access the random numbers from Gaussian distribution, the command is random, not random.
Okay.
And yeah. Now, once you have an array, let's say here there's something given as A, B, C, D, or and you want to make some choices out of that array, right? So I want to pick 3 elements. So now and I want to pick 3 elements without replacement. So that's given by this command np.random.choice and choices of 3. And if you set replaces false, then you get this thing. At max, you can print the size of the array with this. Now, when you say replace is equal to true, you can print any number of this. Right? 5 entries A, C, C, A, A. Yeah.
Sir, can you come again? Your voice is actually like hearing like far away distance.
Okay. It's been like that from the beginning, or just now it happened?
Yeah, it is happening, but
okay. What I'm saying is, if you want to pick the elements without a replacement, right? This is the command. So random.choice. You specify the array from which you are picking the elements and number of entries, and replace is equal to false. Right? It is first it will be B and A. That they are different because you said that you don't want elements to be repeated. And random choice with replacement is you are giving the freedom to repeat. Every entry can be repeated, right? And yeah, as I said, these are the 2 most popular used distributions: uniform, normal, and there are others as well, exponential, Poisson, Riemann, chi-square. Okay, so how now when you do experiment, you want to replicate, let's say you've done something and you want to reproduce the same outcome, right? How do you ensure that? So you have to set the seed before you start an experiment. Right? So when you run again with this seed, you'll get the similar this thing. Okay. So it is something like this, right? You set a seed and you run, you enter random values. You again set a seed, again you assign it, again you do a np.random.rand and then you print it with the same numbers.
So just wanted to check if we are calling the random in the process of running, do we need to do any of the hard disk operations or?
Can I come again? What do you mean by hard disk?
In sometimes in the olden days, if you are calling a random number generation, the function is expected to do some hard disk operations. Based on the timing, it generates a random value.
Probably internally that might be the case. Or typically there are something called the pseudo random generators, which is a different topic altogether. And as far as you're saying timing based, I doubt that. It cannot be timing based because you want to reproduce. Today you ran an experiment, you want to reproduce. Tomorrow you want to run at a different time and you want to see the same result. And, I don't think so. That's a good idea.
Okay.
Yeah, again, linear algebra operations, right? And most of the commands of performing linear algebra are found in Linux, this module. You can solve the linear systems of equations, compute eigenvalues, eigenvectors, right? Matrix factorization, all those things. Finding determinants and inverse, matrix inverse.
Sir, any difference between num arrays and eigenvectors?
What? Num arrays and eigenvectors.
And eigenvectors doing.
Eigenvectors, yeah.
Yeah, is there any difference between the numpy arrays and eigenvectors?
Eigenvectors is a property of a matrix. It's a property of a matrix. Let's say a row, or not even row. So trace, trace of a matrix.
Okay.
It's the sum of the diagonals, right? It is something specific to a particular matrix at hand. It is nowhere related to our number. Okay.
It's a mathematical concept.
Yeah.
Okay.
So as we said, we'll find the eigenvalues and eigenvectors. So this is the command to use. It gives us the eigenvalues and eigenvectors. So there are so many things that you can do here. So norm is Euclidean norm, right? You just measure the length of the vector. And SVD is singular value decomposition. You should know it. If you don't know, I encourage you to read it because you may end up doing something on this SVD going forward. All right, as an event requirement, I can.
So is it a determinant, sir? SVD is a determinant of a matrix?
No. It's the so SVD is nothing but the you obtain SVD by taking the eigenvectors of the matrix A transpose A and A transpose. So it has the two. So any matrix has an SVD.
Okay.
So if A is there, right, it can be decomposed as the sigma B transpose. Now U is M cross N, right? So this is M cross N. This is M cross N, and this is M cross N. Okay. So any matrix admits these decomposition. That's the best part.
That means you're decomposing A into two matrices.
3 matrices. This is a diagonal matrix.
Okay, diagonal matrix. Yeah. Okay. And if I multiply all three, I'll get back K.
Yes, exactly. You'll get that. You have to get that.
Okay.
And what else?
So is there any rule to divide into three portions?
divide it into.
Three matrices. Do you follow any specified rules?
No. Actually, this falls into a broad concept of diagonal visibility. So, I mean, I really would like the matrix to be as as close to the diagonal matrix for analyzing the properties in general. And that's by no means, the best possible explanation. Why do you want to do this? But yeah, as close as to the diagonal matrices.
Can you just come to a little near to the microphone?
No, I'm already using headphones.
Oh, okay. Sorry.
Yeah. Yeah. So this has a property of U being orthonormal. U and V being orthonormal.
Okay, you will be orthogonal. Okay, got it.
Orthonormal. So there's a difference.
Orthonormal. Okay.
Orthonormal is each vector magnitude is one. This is also orthonormal.
Okay.
Okay, so you have more than, I mean, a lot of these things, norm, SVD, QR, you can solve these plus problems as well, I guess, and eigenvalues, and I don't know whatever this means, tensor solve tensor. Yeah, so let's come to the final part of our notebook part, this thing. Image as a matrix, right? Images are nothing but matrices or arrays. Typically, color images are 3D arrays, and gray images are 2D matrices. Right? See this thing. If you see the values, they are between 0 to 255. And let's see the shape of this thing. Right? The type is I mean, this is generic in the array.
India.
We have 3 dimensions. You see 3 dimensions. Each dimension, if you know, RGB is split into red channel, green channel, and blue channel, and you can visualize them separately using this thing. Right. And when you jointly view this, is what we see like this. And yeah, you can convert this to gray, right? Like this. Gray is like 0 black to white, and in between you have gray, right? So this is what it is. And yeah, all the entries will be from 0 to 255. Typically, they are normalized from 0 to 1, right? You divide it by 255, that's it. Yeah, image as a function, right? This is an interesting plot. They have taken this thing, the plot of the image of a horse, and they showed a grayscale image. Now, the point is, they are viewing this as a function. Now, your x and y is the axis, and the pixel value at a given x comma y is the function on that location. So if you see the horses are all zeros, whatever is not horse is the peak, is the 255 or 1.
Is 250.
Normalize it is 1, if it's not doesn't normalize it is 255. Okay, so now that's what you're saying. Right? The true is nothing but the first the white part. Whatever is black, it will be false.
So if I in fact print this as a regular size, the false values will almost look like a heart.
Exactly, I'll show you that. And that's what it is, right? You can see this, right? These are zeros, false values, and these are ones. So the whole that is created is the house.
So what is the third axis, sir?
Is the intensity of the pixel, right? The value, the grayscale value. This value, right?
Correct,
These
but
values are value. This is the third axis.
I mean that you normalized into 0 to 1. Okay.
Between 0 to 1, right? So let's say 10 comma 20. I want a value of 10 comma 20. Just go to 10th row, 20th column and see the value. That's it. That's the third axis. The value is the third axis. Location is nothing but the pixel. Okay.
Okay, the X and Y axis are actually intensity values or it's the resolution
No,
of
no,
the
no,
image.
no. Location
Okay,
of the
the X
image.
and Y is a
And,
resolution, yeah, pixel resolution,
yeah.
and Z axis may be the intensity value.
Yes.
Okay. If we get a top perspective, it looks like a horse, I guess.
Yeah. That's the whole. Whole in the sense there's zeros, right? All are zeros. So the
Yeah,
whole is a horse.
yeah.
And yeah, typically there are some transformations. So here, if you see, it is the original image, and they increase the intensity. I think they increase the pixel values. The second one, right? They Yeah, you increase the pixel values, they you end up turning to white.
Sir, are
And
we
when you flip
wrapping up
the
when we are doing increase operation? Sorry to interrupt. Is it okay to interrupt and speak, sir?
yeah, sure. Yeah.
Yeah. Are you wrapping beyond 255?
Yes, we clip it. We don't wrap, I guess. We clip it. Wrapping is a very dangerous thing to do
So flip it.
because
Example means if it is a pixel is 250 and adding 40, the
yeah,
resultant
you
pixel
make it to 250 only. 255 only. Yeah.
254 only. Yeah. Okay.
255. That's the max value.
Max value. The reason why I'm asking is see there is a white powerhouse on the image and the left image.
Right,
Adding
right.
let us say something is becoming black. So I just got a doubt.
Probably um, mm, maybe it's doing that, I guess. But ideally that should not be done. If you just want to
Should not
increase
be
the
done.
intensity, yeah, that's not intended. Maybe there is something to mention, right? Maybe by default it's probably worth going, but yeah, that's not intended. I mean, I wouldn't do it because by increasing intensity, I don't want to change something white to black.
White to black. Yeah. That is not supposed to happen. Yeah.
Yeah, yeah, maybe you're right. Yeah. So this is the flipping the rows, right? You just do these image upside down. That's it.
Yeah.
So as I said, you can do the row flipping like this with this command in the earlier um, notebook sections. And flipping columns, just flip the columns and you end up having the new. Yeah, I think that's it. And yes. So, here we are declaring the max value as 255, min value as 0, and H2. What we are doing here is we are negating the image, right? So if the image has a 255, that will assign it value 0. If the image has a value 0, it will assign a value of 250. It's a
Something negative transformations.
exactly, yeah. That's it. And linear contrast stretching, actually, the thing that is there here is we probably retain the same thing in the sense, um, what I meant here is the operation as I think in presented here, uh, since I min is 0 here, right? And it will mostly, I think, we will end up seeing the same image. Ideally, it's like linear contrast stretching should give low increment to the lower pixels and higher increment to the higher pixel intensities. That's intended. Not sure if that's happening. Um,
So relatively, image max and image min has been relatively calculated by transforming into IMIN value.
Right.
So relatively doing a contrast. Image,
Yeah, you can say that.
image min is 61 in this image. Image has a max value as a 250, not 255.
Right.
So that has been relatively adding it to the image with image minimum.
Mm, yeah, but visually it's not that.
It's not really contrasting actually as such. But contrasting, you're supposed to give the given range that you're stretching. But it is here, it is taken the formula whole image min and max as a contrast. Are you getting my question, sir?
Can you come again?
Certain pixel range in the input image, grayscale image. Let us say I want to contrast stretch the range, let us say 100 to 150. That can also be done. But here, image min and max is taken so that the borders at this difference are get stretched.
Yeah, I mean, it's hard to make make it out. The
It's very
difference.
hard to make it because contrast stretching is essentially it should shade down the borders between the edges in the scenery images because you're stretching the contrast. High contrast means the borders are very clear. Just correct me if I'm wrong. And those borders should actually little bit fade. It should happen because we're stretching that contrast.
I'll see what probably by adjusting something if I can show a better uh, view of this. Um, yeah. So coming to another operation is averaging. Right. So let's see what is this. Um,
Why do you use image averaging? Like on what purpose?
I'll show. I'll show. So basically, what we want to do is we want to remove certain high frequency component in an image. Let's say, right? Um, Typically, we use low pass filters, and low pass filters are sort of averaging things, right? So that's the main reason for averaging the image, right? Some undesirable high frequency components, if there are in image, we have to remove. So so now how the averaging is done is using a kernel, small, it can be small 2D kernel, 1D kernel, or whatever. Um, so when you do it, what happens is the image size gets reduced by the filter size. So to avoid that, they add some more zeros to the border, so that after you do applying the filter, the image size is still remains the same. So let's see. So this is how the averaging effect looks like.
Okay, it's
Okay,
average
so
filter. It's average filter with padded values.
right, it's just a moving average, I think. What is the this thing? What is the window size? Yeah, I think window size is 15. And they're averaging it the neighboring 15 pixels.
15, yeah.
So basically, what happens is any averaging effect, the effect of averaging on a for a given image is blurring. the sharpness will be gone.
Yeah, and the sharp edges will go up.
Yeah. So that's the typical
Smoothened out.
signature of averaging. You can if you see the blur, you can say that it has been smoothened or averaged. Okay, so there are two things: convolution and cross correlation. So let me quickly explain what is convolution and cross correlation. So let's say this is my x of n and this is my h of n. There are two signals. I'll explain in 1D. Similar thing translates to 2D. This is sequence. And this is also a sequence. Set of numbers. I'm just representing like this. 1, 2, 0.5, 0.4, whatever. Right? So the convolution operation defined between two sequences, something like this. Zero to say L. L is the size of this sequence. Okay. This is my convolution operation and cross correlation operation is nice. Yeah. So these are the convolution and the cross correlation operation. And let's go to the notebook. So now we are creating an image, 7x7 image. It's sort of an impulse, you can assume, an impulse signal with one in the center. Okay. So
Okay.
if we do a convolution operation using an impulse signal, you end up getting the same signal back. So that's why it is called as the impulse response. Uh, what I meant was, so basically, yeah, you create a filter here, some filter. This is a visualization of your filter.
So that link space does a convolution all by itself, which
No,
actually.
no. Linspace is not this thing. It generates a number with 9 numbers between 0 and 1. Equally says between 0 and 1, and the resize it to 3 and 3, 3.
So what is that operation that you applied to get that output image? Can you just go back up little up?
This one.
This is image show
one.
as it is. Yeah, pulse you're showing, impulse you're showing
Yeah,
it.
here also the same thing. Same thing, nothing. Just reshape and view it. That's it.
Just reshaped it. And this is the filter that you have taken. This is a filter.
Has created a image, 9x9 image, and then it created a filter of 3x3.
Right.
Yeah, 3x3, correct. Yeah.
And yeah, this K is some number. It's used for in the writing the code files.
No, that is a formula, right? Filter size minus 1/2 is so many bits to be padded. I think so. Please correct me.
Yeah, you can interpret it that way. But yeah, however you implement it, right?
Yeah,
So
it depends on the implementation.
you can interpret it. So this is how you perform the cross correlation operation, and you get this. And the point is, the key point is, if you do cross correlation using the with a filter with an impulse thing, right? Impulse signal, your filter will be flipped.
It's a
Okay,
horizontal. It's a horizontal
it's flipped
flipping.
completely, horizontal and vertical flipping.
Sir, I
Yeah,
have a
convert the
question
filter.
regarding this.
Yes, yes, yes. Both it.
Yeah,
My
yeah,
question
yeah.
is, from the formula perspective, we have seen the difference between the cross correlation and the conversation.
Right,
But
right,
if we talk about the application perspective, what is
right.
the major difference between cross correlation and conversation?
Oh, see, in general, when you deal with this thing, right? Okay, from the application point of view, if you go with the signal processing applications, typical image processing, signal processing application, we always use convolutions. Okay,
Yeah, you are
because
right.
right, and the cross correlations are used when you say applying deep learning filters on an image. They use cross correlation. So the key disadvantage of using the cross correlation is this. And what is this? Yeah. So
Yeah,
something like this. A convolution, let's say,
yeah, it
D
provides the two flip
convolution.
image cross correlation, but the conversation provide the exact replica of that image. That's the
Right.
difference. But my question is related to the application, the practical application of cross correlation and conversation.
So practical application of correlation is straightforward. Uh, in the signal processing in signal processing context, I can give you. You want to match how similar a signal to another signal. Let's say, right? There you want to correlate these two signals and see how well it is matching. So that's where you use the correlation. Convolution is
Okay.
something to get the impulse response of a system. Let's say, there is a system, let's say, and you pass the signal and you want the output, right? So how do we do it? So first, are you familiar with linear time invariant systems, LTI systems or something? Anyone of you? So let's say, what should I say? How should I say? Let's say some simple. Um, how should I put it? So there's some system. We are giving some input, and let's say this system is doing something to this input. H. Okay, and so how do we find this H is when you just pass an impulse signal, and what you get out of Y is nothing but H. So that's why this H, if you notice what they say in this thing, linear systems thing, H is the impulse response of the system, yeah, right? Why do you say? Because this is excited by passing your this thing X, and now for any other input X, you can compute Y by convolving X and H. So you obtain Y by convolving X and H, not by cross correlating X and H. The cross correlation is used to find the similarity between two signals, and convolution is used to find the response to a given input through a particular system. I
Somehow I
try to
feel
explain.
Yeah, somehow I feel cross correlations, the number of computations may be less compared to convolution.
No. They are perfectly same. To be
Because
precise, it,
you might have to rotate 180 degrees, right? Extra one step you have to do.
I mean, that's fine. That's fine. You can access indices accordingly. That's fine. That's perfectly fine. And yeah, I think that's it. So the same thing for cross correlation, right? Okay, so then probably conversion you end up getting the same thing, same response, right? So that's why this is called as impulse response. And separable convolution, I'll tell what it is. I think maybe this very few things we can just skip it in the interest of time. Uh, Separable convolution, I'll tell what it is. In we will solve few problems. Um, is there anything that is important? I think nothing. So Gaussian kernels are nothing but a special kind of a low pass filters, the kind of averaging. Okay. Yeah, I don't think so I missed anything that is important.
So just a
Sir,
small question.
maybe I. Okay, you can ask. I'll ask.
Sir, one
Yeah.
question is, what is the formula they use? The input image signal convert into a Fourier transformations.
Huh. Yeah.
How
I
do
don't.
they how do they convert the image into the Fourier transformations?
This is a simple kernel, right? Okay, there is a question on computing the Fourier transform. Okay, let's try to do it next. Okay, so this I'll upload this notebook. Please go through, that is important because whatever I told on fly I have told, but it is best if you run every cell and understand why it is.
Sir, maybe
Okay.
I missed out. I joined because I joined late. But the image in the fifth question of the assignment is not downloadable because the library has already updated the image database. That's why this image is not available in their database now.
So I'll raise this thing with concerned team dealing with this course. If possible, with Professor, right? And yeah, so but thing is, there is this instruction that we are not allowed to solve your assignment problems. We will solve some similar problems, but not the actual assignment problem. Okay. Hello, clear?
Hello,
Yeah, can you hear me?
pardon? You are
Can you
not
hear me?
audible properly. Can you please repeat again?
Yeah, what I'm saying is we are not allowed to solve the assignment questions. Maybe similar related questions we can solve, but not the exact assignment questions. And your concern, I'll try to.
Okay. Sure. Thank you.
Okay. Okay. So let's solve some simple questions. Right. You can see the screen, right? Yeah. So this is nothing big deal. I think all are the valid image formats.
RGB?
RGB, they are all actually.
They're all formats are okay.
Yeah.
They're all valid formats. That's it. So now,
What is the output for converting the sequence
yeah,
101 with 1 minus 1?
0 minus 1 with this thing. 1 minus 1 and 0 2 6. Yeah.
Same?
So how come? Okay, let's solve this. 1 0 minus 1
1.
minus 1 0 to 6. You know, what was this? 1,
1 0
Zero.
minus 1. 0
minus
minus
1.
And what is this? Forgot. 1 minus 1, 0 to 6. 1,
1 minus 1, 0
0.
to 6.
2.
6.
Okay. So basically, I'll solve this using, I don't want to solve using this thing. Call this as h and call this as x. Okay, you can find this thing x of n minus k.
Go away, minus 6.
K goes from 0 to 2. Why? Because length of x is 3. And 0 based indexing, so it's 0 to 2. Okay, this is why I have. Okay, so I don't want to solve like this. And since this is a convolution of this thing, right? This signal I can represent it as delta of n times 1 and 0 times delta of n minus 1 plus minus 1 times delta of n minus 2. Delta n is this thing, discrete impulse. Is 1 when n is 0, 0 otherwise. Okay. And I'm convolving x of n with a bunch of impulses. And remember, whenever you convolve x of n with, say, delta of n minus k, the output will be shifted by x of n minus k. That's it. Okay, so that's why this is called as a time invariance. So what is the time invariance is? If I provide impulse at time k, right, I get the same x of n as output, but x of n will always be shifted by that much delay, k unit delay. Okay.
So here, what is n? What is k, sir? N should
N
be
is
our
your time. N is your time. So this is n.
1 minus 1, 0 to 6.
Yeah.
And k will be?
I mean, so in this context, there's nothing like n in whatever the way I have framed here. There's nothing like n and k. Right? It's both are n. Okay. Actually, you were given two sequences and you asked to find a convolution of it. So by, I mean, there is nothing. There is no implicit meaning to k here. Okay. It's just anything. K can be L also. There's no this thing. Okay. So what happens if I do conversion with the original delta? I'll end up getting x of n. Because this is 0, it doesn't matter. 0 times convolution of x of n minus 1. Plus what happens to this thing? Minus 1 times x of n minus 2. Okay, that's it. What you do is do this thing 1 minus 1, 0, 2, 6. Slide this by 2 units. Right? If you slide this by 1 unit, it will come here. Slide this by 2 units, it will be like here 1 minus 1, 0, 2, 6. So 6. Multiply this by 1 minus 1. That's it. And add it. Add them. Add it. That's it. So what
So
do you get? 1.
if you solve this equation, it becomes plus 2. So it becomes essentially plus 2. That means the 2 pixels next to that are just adding to 2.
You're just adding. So when you
Adding.
perform
Okay.
it increases.
Okay.
In correlation, we add. In conversation, we subtract.
No. Both we add. Okay. So the kernel in convolution is flipped, right? So how should I say y of 2 if I want to compute y of 2 by based on this equation? Okay. So what should I get here? K goes from 0 to 2 x of k times x of 2 minus k. Okay, so here my input is flipped. This is x of minus k you're dealing with. Flipped and shifted by 2 units right. Okay. What is x of 2 minus k? How can I write this? I can write like this in this way, right? Minus of k minus 2. Right? So what do? You flip the actual input to x of minus k and then shift k to right by 2 units. This is what precisely I did. In cross correlation, you don't need to flip. You just keep running one signal on top of other. That's it. Yeah, that's the key difference between convolution and cross correlation. Yeah, so this is another simple question, and let's see what we do. Minus, can remember this. What is this? Minus 1, 0, 1, 1.
Sir, if you don't mind, just go back to that solved problem just for let us take a look at for a few minutes, sir. Previous problem.
Yeah. Yeah.
So 2 times you have slide to 2 times. 1 minus 1 0 2 6 is input, and then started from second pixel, and then you slide 1 2 3 4, and then you just add it up. Okay. But in the convolution, you don't flip to 180 degrees.
You do flip, but I have not. I haven't done that way. I have done in a little elegantly. So if you want to flip and all, you can use this thing.
In the actual output, don't we need to flip?
No, nothing.
Okay, enough of this equation. Okay.
Yeah. Okay, so yeah, let's solve this one, right? Okay. Yeah. So I want a convolution of this. Say this is A and say this is B, and I want to find get a sequence C. I want to know the sum of all the numbers in the sequence. Okay, so similarly, like the way we did it, -1, -1, 0, 1, 1, that multiplied by 1, right? The first is 1. And we slide it to the right by 2 and multiplied by 2. So -2, -2, 0, 2, 2. And you slide the original signal by 2 units. That means it's here -1, -1, 0, 1, and 1. So what do we get? -1, -3, -3, 0, 3, 3, and 1. Yeah. What is the sum of all these?
So this has output has a 7 bits, 7 pixels.
Right. So basically, there is a simple way to do this. If it has the sequence length N1, if it has sequence length N2,
Maybe we have to eliminate the first and last element.
N1 plus N2 minus 1. Overall length post convolution should be this much. Convolution or correlation. Right? This should be the length of the sequence.
But sir, I read somewhere that convolution always reduce the number of pixels or the also reduce the length of the image. Is this the right statement?
I mean, it depends. Ideally, it should increase, but the way we do is, if for the images is little bit different in the sense, we increase the original size of the image, and then we try to put this kernel. Uh, so basically, for image, how they do it, you don't want to cross the borders, right? So here you perform only when this filter fits within this image. But what you are saying is true. We'll get to that, right? When you apply a filter, which fits within an image, and you move the filter, right? With a slide 1 or 2, this size decreases. Yes, but this is a generic. This is very generic thing. So here, so ideally, only this part should be considered for images. For
Sir, if you
image,
want to get a mark for this, what should be my answer to be written, sir?
what?
If you give such kind of problem, and if I want to get a marks, and what should be my answer? I should write in the output. This
I
in the
don't think
settings.
so. We will be having such ambiguity. For images, you have to do the convolution within the image. If you are given a sequence and you ask to perform convolution, you have to do this.
Okay. Because there's a lot of ambiguity in this, so
Yeah, I mean, nothing much ambiguity, man. I mean, given an image, you have to fit the kernel within the image. You can't,
yeah.
uh, exclude the certain part of image and put a filter, you know, like that.
Okay, so we assume we're padding and we're doing the operation.
Exactly. They should mention a pad and then perform, or if they don't mention pad, you have to reduce the size.
Yeah.
Okay. Uh, okay. So what is next? Yeah. Actually, I want to have further discussion on this. What is the sum of all these things? What is the sum of all the elements? It is zero. And it doesn't happen by chance. Okay, this was chosen like that. So whenever you have a signal that is antisymmetric, that means x of n is minus x of minus n, or odd signal, let us say. Odd signal, right? This is an odd signal. Even signal, it should be plus. For any odd signal, if you convolve with a symmetric filter, this is a symmetric filter, right? It is symmetric with respect to zero signal, the middle index, right? And you will end up with uh, uh, odd signal. Okay, and when you sum an odd signal, you end up getting zero. And the same conclusions can be drawn to matrices. If you are given, or images, right? If you're given a 2D image with a matrix A and another, say, filter F, which is symmetric across rows and columns, such as this Gaussian filter 1, 2, 1, 3, 4, 3, right? It is symmetric. And you have given an image such that A transpose is minus A. Skew symmetric matrix. This is called a skew symmetric matrix, and diagonals are zeros. That is image. If you do a 2D convolution on this and you are asked to find the sum of all the elements post convolution, that will also be zero. Only reason is this: when you convolve an odd signal with an even signal, you end up getting an odd signal. And for odd signal, by definition, some of the entries has to be zero. Okay.
Any real application, sir?
No, it's just a problem. For you
Mathematical
to
thing.
anything.
Okay.
Yeah, that's it. Hmm. Yeah, so the another thing called as the kernels are separable. Separable kernels means what I meant was this thing. So suppose there is some kernel 121 and 242, let us say. What is the outer product, okay, of matrices. So what I get here is the 242, 484, and 242. So basically, if we can decompose this matrix as the sum of two outer product of two rank one matrices, two rank one tensors, right?
Then convolution becomes some less operations.
No, nothing. Yeah, basically it will become little computationally cheaper. Basically, what happens is if you can decompose kernel like this, you can perform this as the horizontal convolution and this as the vertical convolution and the image and get the same result as if you are convolving the entire thing. I think it has some computational benefits. Okay, so such a kernels are called separable kernels. Okay, if you can decompose a kernel like this, it's a separable kernel. So the question is this kernel separable? Okay, the answer is no. Because for separability, you need the rank one. Here, this is not rank one, it is rank two. This matrix is rank. Okay, that's the simple thing. You verify why it is rank two. I'll upload this question sheet there, along with the notebook as well. Okay. So finally, the last question. So I'll explain what does this mean. Yeah. So this is the signal, pulse signal. Okay. So this is minus 3/2 to 3/2. And this is 1. This is 3. Right. So I want to complete the Fourier transform of this signal. The signal Fourier transform is simple. X of t e power minus j.
So T is a time series, sir.
Yeah, it is time. 2 pi ft. And integrate with respect to variable time. Okay, just if you do it and you do it minus 3/2 to 3/2, and what you get, it is 1 only in this side and 0 everywhere else. E power minus j to pi f t. Okay, if you solve this, you end up getting this thing. E times sin of t. Okay, what is sin of x? Is sine pi x, right? Sine pi x pi x. That's it.
So essentially,
Okay.
just to my interpretation, please correct me. You have taken an image at two time snapshot. During the time snapshot of minus t2 to minus t2 plus t2, you consider
Yeah.
all these images and then you transform the image into Fourier.
No, there is no image here. It's a single, it's a one-dimensional this thing. Okay. You can have a two-dimensional this thing also on say another axis, say Z, and consider this in a discrete domain. And if you do the same thing, you'll get sync on another
Another axis.
dimension. Yeah, another axis. F is
So
only one axis, F1, and if you have another time axis, it will be F2. Multiplication of two syncs. Okay. Again, this is also, and this is typically a very, very important transform in signal processing, especially for communications. Right? Otherwise, I mean, it's fine. I mean, this is just to make you solve this problem. That's it.
So in general, typically, how do you transform the input image, which is of 2D nature, into Fourier
Yeah, same
transform?
thing, same thing, same thing. This is the definition for one thing, right? So if I have T1, T2 here, right? I have F1, T1, and another exponent for minus j 2 pi F2, T2, dt1, and dt. That's it. That's for 2D.
Okay, that essentially means you're integrating the same images from minus T2 time to T2 plus T2 time. You consider all
Right.
those images,
In
and then
this
you transform.
in this problem, it is like this. In general, it can be
In general, in
any
general.
way to image.
Okay,
And
okay.
when you speak about images, we don't call it as time. We call it as a spatial domain.
Spatial. Okay.
Spatial domain, right? Okay. Any more questions?
So my double integration will start from an x-axis 0 to m resolution, and y-axis becomes 0 to n.
Yeah. It will not be having integrals. We'll have a summation because it's a discrete.
Summation. Yeah, because it's a spatial domain, you do summation.
Yeah. Correct.
And what will be my
Okay.
F1 and F2, sir? Any chance?
F1, F2 is your is another domain, right? It's a frequency domain. What we typically call as frequency domain. So here I call as x of F1, F2. That is what is the transform domain. Okay. So here time axis going to frequency axis. Okay.
Sir,
Yeah.
sir, we have 15 more minutes now, sir. Can you please revise whatever we have done so far?
So whatever we have done so far, we have done a lot of things today. Okay, so
Uh,
first we have done your NumPy arrays and what are the attributes for an array, followed by a single dimension to two dimension to multiple dimensions. Then we looked into how do we access the entries of array, right? One dimension or multiple indices for a 2D, and what else? Um, Yeah, again, the another crucial thing we did was the operations on the arrays. Okay, addition, subtraction, all those things. Okay, and then we went to some logarithmic, exponential, those functions. Okay, again, we went to an important concept of broadcasting, and where uh, basically we add a single array to a matrix and it gets broadcasted to all the rows. I especially urge you guys to run this broadcasting part and understand the explanation here. Because I had to cover so many things today. I went a bit fast, but I agree. And yeah, again, manipulating the arrays, such as resizing the shapes, flattening it, and we went to see the Ravel, how Ravel is different from flatten. And we went how do we stack different arrays, right? And split I did not go because it's not. I haven't much used split, but typically stacks are very much used. Resize, repeat, and unique are very frequently used operations. And again, we went for indexing the multiple dimensions. There's nothing fancy about it. It's the same as the same what we have done earlier. And random number generation, then we have discussed. Especially what we frequently use is randint, rand that is uniform, random that is normal, standard normal distribution. And then we went for choice, like from an array, and with replacement, without replacement, those things. And again, we went on discussing how to for replicability of experiments. how do you want to set a seed, right? This is the command to set the seed input.random. Then we went on discussing the linear algebra topics, determinant, inversion, solving linear system of equations, eigenvalues, eigenvectors. I haven't discussed what is eigenvalue, eigenvector completely. I'm assuming you guys know. If not, please read and just go to Wikipedia and read. That would be good. And we then interpreted images as matrices and performed certain simple operations, like inverting and visualizing this RGB of an image, and then inverting, viewing image as a function, right? That's what we saw, this one. And this just transform the image and yeah, flipping rows, columns, increasing intensity. This is a black and white thing. And this I need to check, it's not that visibly looks the same. Yeah. And yeah, applying low pass filters to image, what is the impact that can have? Is it blurring of the original image, right? That's what the low pass filter does. Then we discussed, I think, in depth in the problem solving, the difference between cross correlation and convolution. Okay. What else? I think that's pretty much right. Gaussian kernel is where I just separable kernel I have discussed detail, right? When they call a kernel, it is separable. And Gaussian kernel, I just left it. It's a simple. It's just a low pass filter which is a special property. Yeah, this is what we have discussed. On top of that, we solved, I think, the problems which I'll upload this thing. I think, yeah. Anything else, guys?
Sir, it's off topic, sir. If you are off topic, sir, if you permit us, we can form a WhatsApp group among students so that we could learn from each other. If you permit us.
I am nowhere to. I don't have that authority to permit you guys what to do. If you guys are friends, I mean, nobody is stopping you, right, to do that.
Okay, sir. I'll just type
but there is no platform to connect us, right? Only other than this one. Is there?
Yeah, WhatsApp is a good suggestion. Even there are other platforms like Telegram is also a platform where we can connect.
Yeah, but to be honest, right now we don't know anyone, right? And there's no mobile number or anything, so somewhere one can take an initiative or something like that.
I have sent a message of my WhatsApp mobile number, sir. If you can able to see my message, just see, sir.
Actually,
yes, I'm able to see.
I cannot be.
That is my number, sir. Just make a note of it and reply to me, sir. I'll just create a group.
Okay.
Yeah, I think I'll have this thing. Yeah. Actually, is there anything that you guys can ask NPTEL to do this? Because I cannot be a part of this group. I don't think, I'm not sure if they allow.
Sir, the reason is there are a lot of things, the prerequisite knowledge is not there, which is actually a hindrance because everybody is occupied with their professions, family, kids and all. I know it's open secret, nothing else. But if one person knows some prerequisite, they can ask, I know this, I don't know this, then probably we can patch up the prerequisite. That will help us collectively just to level up our understanding just one step.
Yeah, I mean, I am fine among you guys forming the group. I don't have any problem with that. But if there is something that you need to take permission from these independent people, please just take it. Right?
So, okay, sir. Whom should we ask, sir?
I don't know because you must be having some names, right? Contact.
Okay, okay.
You're creating the group?
I'm creating the group, sir. 74474.
Okay, okay.
First number in the chat. Or rather, if anybody wants to take that initiative, I'm okay.
I am taking. Okay. I'm
Okay,
just
sir.
creating the group.
Okay, sir.
Okay, guys. So I'll leave. If there are anything we'll meet next week and we'll discuss.
Okay, sir. Thank you
Okay.
so much.
I
Yeah,
am
yeah.
creating the
I
group
hope
with the
it
name
was good.
Deep Learning.
Sir, actually, one more thing. Other schedules also there, right? Is it a repetition of this same course or only
Can you come
in
again?
that mail? No, other schedules also in the initial mail it comes, right? Or only one session is happening regarding this, or other repeated sessions are happening?
I think this is a repeated session only.
Okay.
The course is repeated. It was offered probably sometime back.
Okay, thank you, sir. Thank you.
Okay, guys. Bye. See you next week.